Okay, in this video, we want to introduce the concept of implicit differentiation and then use it to solve a relatively simple type of problem. To start with, suppose we had this. Suppose we said that we have an equation where y equals, say, 9 times x to the 6th plus 21 x to the 4th minus 7 halves times x squared minus 113 times x minus, say, 7 over 161. And you want to find dy dx. Your first thought would be, well, that should be pretty simple, or pretty straightforward anyway. Dy dx would equal 54 times x to the 5th plus, looks like 84 times x cubed minus 7 times x and minus 113. And you're right, that would be the expression for dy dx. That's what you've been learning in your calculus course all along. One comment we would make is that, for example, when you're taking this derivative here, it's 54 times x to the 5th power, and then it's dx, but we don't typically write that down because that's just 1. Or over here where we had minus 113 times x, it would be minus 113 times x to the 0 power dx, but we usually don't write all this stuff down because this is just 1 and this is just 1. But if we had somewhere in here another variable, say 3 times z to the 5th power, then it would be 15 times z to the 4th times dz dx. And then, in this instance, we have to make sure that we remember to write this down, because this clearly is not just 1. And we bring that to your attention because when we start doing implicit differentiation, it's important that we remember how to do that correctly in that step. Now, suppose that we had this kind of a problem. Say that we had x squared plus y squared equals, say, 139. And we want to solve for dy dx. Now, the way the equation stands right now, this equation is different from this equation. Here with this equation, we stated explicitly x equals this plus this minus this minus this minus this. And this is what y is equal to. That's all in terms of that single variable x. Here we have an equation where y is just one of the variables in the equation. Now, we could, this is simple enough that we could write it explicitly as to what y is equal to. We could say, well, y would equal 139 minus x squared. We would take the square root of that. And so now we wrote this explicitly as to what y is equal to. And of course that's 139 minus x squared to the 1/2 power, so we could go ahead and calculate dy dx that would equal 1/2 times 139 minus x squared to the minus 1/2 power times the derivative of what's inside this expression. This would be minus 2 times minus 2x dx dx, which is just 1. So now we could say, well then dy dx what will that equal? These will cancel. So we would have minus x, and here we have this raised to the minus 1/2 power, so that would be divided by the square root of 139 minus x squared. And that is true. And then you might go back up here and recall, wait a minute, this is just y. So this equals minus x divided by y. So for this equation here, we wrote it explicitly in terms of y, and we determined that dy dx equals minus x divided by y. Now, a couple of things you want to say at this point. First, this expression here for dy dx, that's different than what you might be used to seeing. Up here, if we know what x is, then we know what dy dx is. For example, if x is 0, dy dx is minus 113. Here, if you want to know what dy dx is, you have to know what x is, and you have to know what y is. So we're getting a different kind of expression now for our derivative. Now, what we did was correct. There's nothing wrong with it. We get the right answer, but we don't have to do it that way. Let's go back and look at our original equation, where we had x squared plus y squared equals 139. What we can do is what you've been doing all along. You want to find dy dx? Then we'll go ahead and we'll take derivatives of both sides of this equation with respect to x. So this would be 2 times x, and this time I'm going to write it down just to remind ourselves, dx plus 2 times y dy dx equals, and this is a constant, so this derivative of course is 0, and dx of course that's just 1. And it looks like we can divide both sides of the equation by 2, and we can bring this over to here. That'll be minus x, and divide by y, and there we have dy dx. Much easier, much shorter than the other way we did it. The other way that we did it is we wrote this equation so that we had an explicit equation for y. We said y is equal to 139 minus x squared. And we went ahead and took our derivatives. Here we didn't do all of that. We just took the equation as it stood, took our derivatives, and almost immediately then we could figure out what dy dx is. And when the equation is in this form here, and here's our y, and y is like just another one of the variables that's involved with this general equation, and we go ahead and take our differentiation anyway here, like we've been doing all along, And this is what's called implicit differentiation. And we want to learn how to become familiar with this technique because, as you can see, for determining dy dx, it's a lot easier than getting an explicit value for y and working with this to determine dy dx. And if you have a complicated equation here, the implicit differentiation is definitely the way you want to go with it. So that's kind of the idea behind it, and here's how you can apply it to a simple example. In the next video, we'll have some more examples then that will demonstrate how we can use implicit differentiation.